more stuff on it now. A couple additions since Friday. First of all, the fall office hours are actually there now. It used to say fall office hours coming soon. As of yesterday, they are there. And I want to point this out to you. I have specific office hours that are right after this class in my office on Monday and Wednesday, like at ECA. But here are all the office hours that are related to Math 270. And this is like too small. There's so many of them. So you can go see any of the people that are in this list. Some of the people's names you'll recognize from me talking about them being in here. Julia, Derek, Allison, me. But there's also another recitation with more people and more TAs. Morgan, Hedvig, and Barbara are the other working with the other recitation. And then there's also tutors that are specially trained that have either been in Math 270 with us in the previous semester or are like math majors that have worked with us, so that they're all in tune with what we're doing. All the gray hours there are people that aren't physically taking the class right now or working with teaching recitations right now, but they have all been in there in the past. And there's a lot of different locations in gray. Some of them are in Hassayampa and Palo Verde East, and I forget what. Sonora. Okay, I was gonna say SCD. I forget what that one stands for. But yeah, all those you'll have to zoom it in to see all the different things on here. But for instance, today, Morgan had office hours this morning already. I'll be in my office, which is a couple buildings down. ECA's Engineering Center Wing A. I don't know quite what direction I'm facing anymore, but someplace that direction maybe. But yeah, towards the bookstore from here, whatever that direction is once you get outside, but across the street from the bookstore. Hedvig, the later afternoon lecturer, her office is in the same hallway as mine, and she has office hours just overlapping with me, but then going later. There's Barbara, who's one of the recitation leaders for the other section. There's undergrad tutors in Wexler A. So all this Wexler A, also known as Physical Sciences A on some of the older signs around campus they haven't replaced yet. It's kind of where that kind of coffee shop area is. There's like crepes and coffee shop sort of outdoor area with lots of seating outside. There's a door on the outside of that building that goes into the Math Tutor Center. It's right there. They usually have a kind of A-frame standee outside, say Math Tutoring in here. And I believe they are now open. Right, yeah. On Friday last week, they were not open yet, I don't believe. But in any case, all the rest of these hours down here, let's see, we've got in the dorms late at night, in the tutoring centers in there. To get into the Wexler 116 tutoring center, you do need to have your ASUAD. They try to keep it all the riffraff that wants to study math. I'm not quite sure, but scan your ID card at the door. They're there to help you with this. And they check you in. It's just how they keep track of justifying paying for all the tutors that are there. So it's not like we're trying to figure out if you're studying math enough, although we can do that. But they want to keep track of how many people come and go. So they do it by making sure you're in math classes and are going in there for math help. So in any case, take a look at those hours. There should be something that fits your schedule. There's something between, like 8 a.m. and 11 p.m. on a lot of days. Friday, there's no evening tutoring, but I don't know how many of you want to hang out on campus and do math on Friday night anyway. If you do, make a friend that wants to do the same thing, because there aren't tutoring centers open. So in any case, that's a new addition since Friday. Another couple of things that were on here. Let's see. Oh. After every class, and I just put in a header here so it kind of describes this better, but it's that after every class, after I've done typing it up, so it's not immediately because I have to go upload it, but you'll see the date listed. So this was after Friday. Here's the stuff that you need to look at. So here's a list of things that you should do after class on Friday and before I see you again. Some of them are kind of farther out, and I'll keep reminding you of those. But for instance, this said to complete that Canvas quiz number 1 that we used in class on Friday as attendance, install GC. Before Monday, we're going to do a little bit with that in just a few minutes. And then reading to do. There's also some homework here that's not this iMathAS homework check-in. I apologize if you just added the class today. I am not aware of that yet. I haven't had a chance to check the roster this morning, but I will add you into that system so that you can get logged in following the directions there. But that's just to kind of learn how iMathAS works. And then there is a an optional extra credit assignment there that relates to the first few sections of the textbook. The first 2 chapters of the textbook, for the most part, we're not doing too much with. They're kind of like review of a lot of its pre-calculus concepts and earlier sorts of thought processes that build into calculus, but we're not going to cover a lot of chapters 1 or 2. 1 is a lot of working with extremely large or extremely small numbers, some scientific notation, which sounds kind of like that's 8th grade, but there's some kind of cool stuff to do with this where you have to do some complex computations, and GC can actually help with that. So I'll show you some stuff with that today. Makes it easier to deal with strange numbers. But you see in chapter 2 is all about trigonometry. It's a kind of a trig review, how radians work and what sine, cosine, tangent are talking about, what it is that they're measuring. So those 2 chapters we're just going to kind of touch on a couple times. The last section in chapter 1, 1.5, I asked you to read. That one is, it seems kind of like, oh yeah, this seems like review also, but it's really kind of the basis of what we're doing for all of chapters 3 and 4, and 5 and 6 and 7. Constant rate of change we're going to use throughout. So we'll start with the basic end of it, but it's really, it shows up again, that same section does in chapter 3. So in any case, let me show you just the iMath AS really quick. If you log in using your ASU Write, unless I messed up your ASU Write ID, and Newton as your password for the first time, you can change it if you want. But you'll see on here, this is the homework check-in that's due by tonight if you just joined the class. Take a look at it. It's just some questions like how to enter in numbers and how to enter in expressions, and just giving you practice realizing that X is not the same as some other letters, and this is just kind of a description of how this iMath AS works so that you're not getting tangled up with just the key pressing aspect of doing math on this homework system later. So there's some graphing, there's some symbols that you should be familiar with, but there's a lot of helpers built in. If you need to type a symbol, there's like a little yellow arrow that shows up. Let me show you one of those. Let's see. Let me find one that has those. Oh, here we go. So if I click in this box, it has that little yellow arrow just to the right of the box and before it says preview. If you click on that, it gives you some kind of quick math template things that are frequently done. You can also type them by hand, but if I say, oh, I want a square root, I'll click this, and then I want the square root of 5. That isn't what I'm supposed to be typing in this line. But you'll notice if you do that and click save to go back, it doesn't show the symbol, the square root symbol in there. It shows SQRT and then parentheses 5, which means if I wanted to type something like that again, like square root of 7 or something, I can just type it myself instead of clicking. So if you get tired of the click, 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 click method, if you do it once, you can figure out by looking at what it did, what the typing method is for doing the same thing. So if I wanted square root of 5 plus square root of 7, I can do that. And you can see the preview over on the right shows you what it's interpreting your understanding as. So if it's an order of operations issue, like you meant for all of this stuff to be on the top of the fraction, you probably need some extra parentheses in order to accomplish that sort of thing. So the preview is useful for helping you sort out issues with how do I type math, because there aren't all the buttons you'd ever need. All right, so in any case, iMath AS, the homework check-in is right here. There is an extra credit, chapter 1, 1.1 through 1.4, sort of dealing with large and small numbers assignment underneath. And later this afternoon, there'll be a homework number 2, which is not extra credit, that relates to what we're going to start talking about today, but which is section 1.5 material that I asked you to read a little bit about before today. So I hope that some of this already sounds familiar, but I know there are some people that just added the class, so I'm not going to assume that everybody got the assignment last Friday. So let's see, other things on the website. Your recitation materials. So some of you had recitation on Friday already, and you have hard paper copies of these 3 things already, or 4 things, or something. There's lists on here that are kind of keyboard shortcuts. It's nice to be able to type instead of always having to click sometimes. Keyboard shortcuts for doing things like square roots and pi and how do I get a graph, and some tips and tricks for using GC. It's not too hard, and a lot of the GC, the graphing calculator program, a lot of the things you'll need are up in the menus up above, and once you see them, like, oh, well, I'll just hit like caret 3 instead of trying to remember something or another to get the cube, like third power of something. A lot of it's same sorts of things you've typed before, like, like use the caret to get exponents. So it's just a fairly comprehensive list of the sorts of things you might need for our class. There are a lot more things that it can do, and some of them you'll be working with in your next calculus class, 271. But in any case, you'll see recitation documents listed under our current module. So the module, the topic that we're working on right now, goes up through our first test, which will be that early time in September, however long that is from now. And recitation documents, as you get more of them, they're there. So if you want a fresh copy of it, you drew all over it, and you want a new copy, they're going to be there for you to download, print, or just to see them again if that's all you wanted. So I just wanted to point those things out. But for now, what I'd like to do is take a look at GC. So if you could grab your laptop, if you don't already have it out, and open up GC. So I know most of you have probably not done too much with this yet, unless you've kind of poked around in it. But if you just open up the program, it should look something like this, which looks very boring. It's like, okay, what is this? What do I do with the purple square? Well, you can do whatever you want. This purple square is a command. It means we're on a command line, meaning if you type stuff after it, it knows you're doing something with math. So if I do something like 45 minus 7, it has an answer already calculated out there. If I change it to 75, it recalculates it instantly. You don't have to hit enter for it to do numerical computations or for it to start thinking about what it is that you're writing in there. So if I have 45 minus 750, one of the things that's kind of nice about this, it works a lot like a word processor in that you can copy and paste. You can select items and then apply something to that whole part you've selected. For instance, if I select this and then type the parenthesis key, it'll put parentheses around the whole thing I've selected. So if I realize, oh, I want to do something with all of that, like square it, I can have typed it first and I want to square the whole thing. I need parentheses afterwards. I don't have to like backspace or retype it. Just select it all and hit the parenthesis once. When you type parentheses, it automatically comes in pairs, by the way. So it's a lot harder to have mismatched parentheses. You just have to watch what's in them. If I want to square this, I'm just going to hit the caret sign, which on my keyboard is Shift-6. On some of yours, it might be someplace else. I know caret signs, or some of those on different laptops, they move around. But I could do second power, 17th power, negative 6th power. I put this to the negative 6th power. It says 8.14452 e negative 18, which I hope you recognize as scientific notation for small numbers, that e minus 18, just like on, if you've had hand-held TI calculators. That's scientific notation calculator style for times 10 to the negative 18th power. So this is an extremely small number. Now, here, let me make it less extremely small. There we go. I just made it a negative 3rd power. So notice that this is a decimal. It's not exact. I'm sure that whatever that is now, 45 minus 750, cubed in the denominator of a fraction doesn't come out to be a 5-digit decimals with a whole bunch of, like after a bunch of zeros, and it just terminates there. This would be like 0.00000285386 with more numbers afterward. So there's ways, if you need more accuracy than what you've got, I mean, now this is times 10 to the negative 9th. So this is down to the, I don't even know, like gazillionth place. If you need more accuracy, if you want to see more decimals, you can get that. This isn't like stuck with, oh, you only have a few decimals. You just have to go up into the menus, document settings is what I'm looking for, just under the file menu. And in the document settings, it says precision, significant digits, 6. And that's what that, here. What I have here is 1, 2, 3, 4, 5, 6 digits, aside from the power of 10 that I've got. So if you wanted to see more or fewer, you can change it to that. It depends on what you want, but I could put it to 10 significant digits, and then I just see a longer decimal. So just realize that what you see on there isn't necessarily like the whole thing. Depending on what sort of computation, there might be more digits to your answer when we've got decimals going on, so just be careful of that. So more exact form, this is an approximate form. I'm sure there's more digits beyond that. If I were to change my document settings to show me 15 digits, I'm sure there would be more numbers that aren't all zeros that go past that. So if I want this to be as precise as possible, I can use just this expression here. And that's the same in the Math AS homework. On the Math AS homework with the large and small numbers, rather than trying to type in a decimal form for what you got, unless it specifically asks, right, as a decimal rounded to 7 places or something. If you want an exact answer, you can type in the computation to the answer blanks in Math AS, and that way it will have this as accurately as possible as opposed to round it off to some place or another. So let's see, let me do a different computation because I'm tired of looking at that one. You don't have to delete, by the way, I just didn't want to have all this on there. If you want to have a new line, here I'll type it, 94 plus 56. All right, if I want to have a new line of stuff, I have to hit, it depends on your computer, either Command Enter or Control Enter, and I think some of it depends on what version of the operating system you're using on. Maybe both of those work. Yeah, Control Enter on mine, but I think it used to be Command Enter. So one of those two is going to get you a new square, which that new square means new command line. You might do something that's related to the previous result. Like maybe I want to take this and do something else with it. Maybe I want to have 5,700 divided by, which when I have a single number, I can just hit the slash key to get that divided by. It writes it as a fraction. And I want to take this and copy and paste. I can, Control C, Control V, or Command C, Command V, depending on your calculator type, to just copy and paste however messy the expression is or part of an expression that you want to reuse someplace else. You can do sort of Word document things with it. So this one, I can see 38, and I know my document settings are to 10 digits of precision, so I know that's an exact answer because it stopped well before 10 digits. You can tell when it's exact in that way, but just be careful with exact values of numbers. So this is called GC, Graphing Calculator. If you want to graph something, you also need a command line. By the way, the opposite of the other thing you can do besides a command line is a text line. So those, again, is either Command T or Control T. Let's see. Nope, not that one. Where are we? Yeah, so on mine it's Control T, on some it's Command T. It kind of, like I said, I think it depends on your version of operating system you've got. And like even within Macs, it might be different from one to the other. But some sort of button and then a T will give you a line without a square. That means that I'm not doing computations here. If I were to type something like 94 plus 56, it's not doing anything. This is just a text line. So equivalent if you've ever done any computer programming stuff, this is like where you can write your description of what your code's supposedly doing. So if I want to write, the next thing I'm going to do, if I can type today, is look at a graph. So now I want to do a graph, and still doing I've got extra spaces in there, but if I want another command line below this, if I want to stop doing text, then I do that Control Return. So if you hit a Control T, it gives you a text new line. If you do a Control Enter, it gives you a new command line. And then I can start doing math again instead of just having a place to write a description. So if I wanted to graph, just for instance, like y equals x squared. Notice I type y equals x, and you can see down the bottom there's a little blue thing that shows up that says graph. Now, it doesn't say anything else because I haven't hit enter, but it's prepared. It's already doing math. When you put in a y equals, it's like, ooh, you're trying to graph something. It does the same if you do x equals. You don't have to have things solved for y in order to graph them. And it can also graph in other coordinate systems like polar and cylindrical multivariate sort of graphs. But if let's see, I said I want to do y equals x squared. If I want to graph this, I can click on that blue graph button, or I can just hit enter, and then this graph appears. You can shrink it down. There's a little tiny dot here. You can, I don't really want to see that right now. I've got some other stuff to type. You can resize it. You can scoot this around to see other parts of it. And particularly, if I wanted to only see part of this parabola, like maybe I only wanted to see the portion between -2 and 2, I can type domain restrictions in pretty easily also. So all that requires is a comma and then an inequality format for this as opposed to interval notation. But if I just want to see the part of this between -2 and 2, I can add a restriction on like that and then hit enter again or click the blue graph button. And it's like, oh, that looks the same. Well, it does because It's off the screen here, but you can see it stops when x is -2 and at +2. And these buttons down here are zooms for your graph, so if I want to make it smaller to be able to see more of the graph in less space, we can do that. So you can graph equations, you can do computations, and there's a lot of other things I can do also. So I can graph individual points. I can make points that move. So I just changed the end of my domain to n. N is a magical button in here, or a magical symbol in here that's built in. You might see also at the bottom if you do the same. It says N, and then there's this little like arrow, and it looks like a play bar. That's what it is. So this right here, I can either slide it manually or hit play. But I want to look at this graph. And right now it says N, and at the end it says 0.0. And notice my graph goes from -2 through 0. If I take this play bar, I can make it go farther. So I can kind of see what happens as a graph is generated from left to right within the domain when we're talking about x values here. And I can change this x that doesn't, this just said x lowest value is 0. Maybe I want to go all the way back to -2 and only go up through 2. The number of steps is just like, it's a kind of like how many pixels is it going to move at a time sort of thing. And you can make it jump. So if I said lowest value is -2, highest value is 2, do that in 4 steps. I go chunk, 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 chunk as I slide the bar across. It won't move smoothly then. But I can hit play, and I changed n to just be -2 to 2. So it'll just keep regenerating this same portion of the curve. And you'll see things that look kind of like this in the textbook, animated figures where you see a graph being generated from left to right. This is a simple example of something like that, but it just involves using this idea of this slider, this parameter that I can change its value to like look at different pieces of this at a time. So I say, well, I want to go up through some value n. What if n is 1.04? Graph looks like this. So in any case, I don't want to spend all of today on GC, but I do have something I'd like to show you. While you have GC open, I want you to try to do some computation stuff. You'll get a chance to do a lot of graphing stuff in your recitation, either today or Wednesday. So I'll leave some of that for thinking about there. But take a look at this. We've got fun with geometry. We've got a trapezoid and an inscribed circle. So there's formulas for trapezoid and circle areas given below if you want. Oh, by the way, if you want to type pi into the graphing calculator, just type the letters pi, and it turns it into a pi symbol. Forgot about that. So if I type p, it says p equals 1. If I type I afterward, it suddenly turns into a pi symbol. Same happens with some of the other common Greek letters, but this one doesn't have a value. Pi is a constant. Theta is that symbol there. So there's a few symbols that are built in. If you type out their spelling, it suddenly turns into something else. But pi has a value. Theta would be something I can use if I want to graph, actually. In fact, if I want to graph r equals sine of theta, let me zoom in a little bit. R equals sine of theta is polar coordinates equation for a circle with, well, in this case you can see radius 1/2 centered at 1/2 on the y-axis. Not getting into how to graph polar stuff today, but it graphs in xy coordinates, graphs r theta coordinates. Those are the two-dimensional things. And there's parametric equations and a lot of different options as well. But, all right, so in any case, take a look at this and get a command line for yourself in GC. There's numbers 4s, 5s, 9s, and, well, you'll need a 2 and a pi for other purposes, like a squared and a pi from the circle formula. But see if you can write one single expression using only those numbers. In other words, don't do any pre-calculation or type in a formula and have it call up a formula or anything fancy computer programming-wise. But just see if you can put together one single line expression, like maybe lots of parentheses and divide and square and then do something else with it. Whatever you might need to do to see if you can come up with a way to type all this in. Just practice at utilizing GC's, copy, paste, or whatever you need abilities to get an expression for the area between the circle and the trapezoid, those 4 little corner regions areas summed. So there's a little bit of geometry thought process involved in this also. But it's calculus. Let's do some math. Don't have a laptop with you, if you want to look on with someone else to see how this would go, or work it out and see if you can figure out how you would type it. If you're having trouble, let one of us know. You can also ask neighbors. Yeah, so let GC do the work. Don't try to pre-calculate things. All right, so general principle-wise, can anyone give me a description of overall, big picture, what needs to happen to get this area? Yeah.
You need to subtract the area of the circle from the area of the triangle.
Okay, yeah. Outer area minus inner shapes area gets us the stuff in between. So what are we missing in terms of calculating those two areas? What's one thing? Okay, we're missing the height, which would be indicated by the length of these dotted lines here, the distance between the two parallel bases of the trapezoid. How do we find that? Yeah. Yeah, Pythagorean triple. We've got Pythagorean theorem, but these might be familiar numbers. So what's the other number that goes with these? Yeah, it is 12. Now, supposing that you are not a math student that is familiar with these and you needed to calculate this from scratch, what expression would give you that 12? Like, what's in the background? What gave the 12 from here? Because we're supposed to not be using 12, we're supposed to use 4, 5, 9, 2, and pi. So what sort of expression would give us that the length of this is 12? It's a leg of a right triangle, so hypotenuse squared minus the other leg squared, yeah? Okay. Because obviously, you don't have to do it this way, but if you want to strictly follow the instructions, like, all right, I'm not going to use any extra numbers, so I'm going to have just, let's see, the length of this side squared, which would be, oh, it's not even 13, it's 4 plus 9 is the length of that hypotenuse. And the length of the other side is 5, or minus. Let me do this nice way. There we go. So minus the other side's length squared. And that would be how only using 4s, 5s, 9s, and 2s, number-wise, we can come up with that 13. Now, then we're going to do our area formula for trapezoid, area of circle. What's the radius of a circle? Yeah, it's 6. It's half of that. The circle goes all the way from the top to the bottom of the trapezoid, so the radius would be half of that. And so we need that number there. We've got our bases, which are 4 plus 4 and 9 plus 9. So if we wanted to follow strictly the instructions here, using just those, it's going to take a little bit of typing, but just GC-wise, here, let me close this up. Where's GC? There we go. Oh. I'll leave that there. Be useful for me. All right, so control return. There we go. So, by the way, if you noticed in the graph that we had there previously, the circle was green and the parabola was red. It matches the colors of those command lines by them. And if you want to change their color, you can. Because green, for instance, doesn't show up very well. So if I wanted to make it purple instead, I can click on that square and change its color to something else that shows up better. Not important for right now because we're trying to find the area of a trapezoid, or the area of the space between the trapezoid and the circle. So we need those heights, but just using our formula then, let's see if I can, no, 0.5. You could type in various parts at a time and then copy and paste them later. So if I want to do a square root, which is Control R or Command R, depending on your, or Option R possibly, among other things. It's also up in the menus here. Math, got, square root. So in any case, I just clicked on something outside there. So if I want the square root of, parentheses, just type parentheses 1 and it gives you the pair. 4 squared, 4 plus 9 squared. 4 plus 9 squared minus 5 squared. And so you can say, oh, there's that 12. I'm going to just do this as a separate line. And I keep clicking on things with my hand. But if I were to put in the trapezoid formula, then I'd have 0.5 times B1 plus B2, or you can type in 1/2, since I guess it didn't say 0.5 in there. Use those formulas. 0.5 times, you get the idea from here? Okay, but I just want to point out I could copy and paste that. So if I worked it out and I didn't want to retype it, if I were doing B1, oh, that's 9 plus 9, plus B2, 4 plus 4, wasn't it? Yeah, that was the top side. That's B1 plus B2 times, and then I want this height here. I want that, copy and paste. So there we go. And notice if you have expressions like parentheses or roots or anything and you had a time sign, it'll disappear. Just like if you had 3 times and then you put an x after it, it'll write it as 3x. It makes the multiplication disappear. So it looks like actual grown-up math instead of I had to type this way. So it prettifies it kind of as you go. But in any case, that's our area of a trapezoid. We could subtract the area of the circle using same expressions again with maybe this over 2 for the radius of the circle and then square it. But in any case, GC has a lot of power to it, and this is hardly any of it, but it is kind of nice to use in terms of that. At this point, I'm sure it's like, well, I can do that on my calculator. Yeah, you can. There's a lot of other things that we can't. So we'll see a lot more of those upcoming. But just as a brief intro to what on earth these like purple square is for, I hope you have kind of a sense of where we're starting from. But like I said, by the next time I see you, most of you will have seen GC and recitation and worked on more complex projects already. And by the time Friday comes around, all of you will have had a recitation homework assignment that some of you need to be turning in later that day, and others of you are still working on, etc. So let's talk about actual topic of the day that is related to calculus, not just how to do calculus, and that is constant rate of change. So let me clear off this stuff. All right, so calculus is all about changes and how they're related to one another. So just very, very briefly, I don't want to spend a whole lot of time on this. This is like the review from a long time ago stuff, but just some notation I want to insert that may or may not be familiar. When we're talking about some quantity, some measurable thing, whatever it might be, we need to have an expression, some sort of symbol that we use for that. But we can talk about, for instance, in this case, we can talk about, in this case, Z representing amount of space in gigabytes consumed by programs on your phone, computer, whatever you want it to be. But if I want to talk about that amount changing, I can refer to a change in Z by its own new separate variable, and that's what we're introducing today. So, all right, so as your phone states, current programs take up 7.8 gigabytes of space. You download a new app that uses 0.5 additional gigabytes. So how much space is now used by programs? So if, just symbol-wise, this is simple math-wise, but just to introduce these symbols that we're going to see throughout, if we let Z represent the amount of space in gigabytes consumed by programs, we can use this notation, Z with a subscript of I, to indicate an initial value of Z that we're referring to. It doesn't always mean 7.8 by any means, but just in general to refer to an initial value of some varying quantity. And then Z with a subscript of F for a final value of that same varying quantity. We talk about it going from 7.8 to something else. It's not going to 0.5. What is the final value of Z in this particular case? Yeah, 7.8 plus an extra 0.5. You're using up space, and then you put on more programs that use up more space. So, yeah, 8.3 gigabytes altogether. That would be the Z final, where that change, that 0.5, the amount that we allowed our, well, we didn't allow, that it happened to change by, that the amount of space varied by during that process was 0.5, half a gigabyte. So this DZ, we're going to use this notation, same variable with a D in front of it to indicate that change. So in certain classes in the past, you may have also used the Greek symbol delta. That's also used in some cases, but what we're going to use this D. This has a special meaning for us. We can use this then in all cases, but specifically DZ is something that relates to typically a small amount of change, although large and small are relative if you looked at chapter 1. If I have something that's, like a light year away, like half a mile is pretty short. That's small amount of change if I'm thinking within a full light year's worth of distance. So we'll use a DZ to indicate a small change in Z. So in any case, in this problem, as we said, initial value is 7.8, just leaving off the units. The Z part is the number, and then there are units that pertain to it. Z final is 8.3, and the DZ is 0.5. I put a positive there. Changes can have a positive or negative value. Oftentimes we don't think about the positive because you don't typically have to write positive signs, but it is an increase by 0.5. So always remember that D in front of a variable is talking about a variation in, or a change in, or an amount of movement within the variable's value. We're going to talk more in detail about what exactly makes something a variable, maybe next class, which seems kind of weird also, but there's some certain careful definitions we need to think about. So, I've got some symbols that disappeared. All right, we'll work on that. So using ZI, ZF, and DZ, same as last time. And I don't know why those went away. Write an expression for blank and blank. But in any case, determine the value of the unmentioned quantity here. So just like last time, there's 2 numbers mentioned, but there's 3 different things we could be talking about. Initial, final, and the amount of change, where the general concept here is, in this case, an amount of memory used. So if I say at first 3 gigabytes of memory was used, after starting a new program, 5.5 gigabytes of memory were being used, what isn't mentioned of those 3? The DZ, the change, isn't mentioned. But what is it? Yeah, it went up by 2.5 from 3 to 5.5. So that's Z initial is 3 gigabytes. Z final is 5.5, measured in gigabytes. The difference between them, the change final minus initial, is that DZ. So what about in this situation? Got a computer, 14 gigabytes of disk space was consumed by your operating system. You've added programs and files, taking up an additional 40 gigabytes. What's the 14? Initial. What's the 40? That's the change. Just because it's bigger doesn't make it final or something. And so what is the final value, Z final? All right, yeah, so 54 gigabytes are the units on that. All right, we get the idea with this. The main concept to keep in mind, though, is when we're talking about this change in a quantity, you can compute it by doing final minus initial values of a variable. So if I want to talk about a change or a variation or an increase or a decrease, or there's a lot of different words we can use. And there's a whole description in the text on, you'll see all of these different things used. Lots of times, if I just say change, it means like it has to have already happened. But when I want to talk about something that's still going on or still occurring, I might use a different word like variation. How much has this varied like so far? And so all those different words are referring to this same, difference between where we started and where we're going to, or where we might be, depending on the situation. So if I was talking about a variation in x, as x increases, if you remember from the moving GC graph, as x went from -2 through +2, we saw the graph go around like that. So as x varies, we could compute the change in x by taking the final position minus the initial position, or the final x value minus the initial x value at any point in time. But we'll call that dx. If you're doing that sort of how far left to right, thinking about x-axis sorts of values, that dx is a difference between 2 spots. It's not what is my current x value, it's how far have I changed from something else. So dx is always relative to a specific starting position. So what's more interesting, though, is if we get out of this, just subtract 2 numbers, end of story, is if I have a second variable, if I have a relationship between x and y, when I change x, I know y is going to change also. And what we're going to focus on, as I said, is small amounts of change in x. And if you can imagine, even in a parabola, something that's not a straight line, if I look at a very small section, if I'm making small changes in x, parabolas aren't super crazy, bumpy, thick. If you zoom in on a section, it's going to look pretty much like some straight line, just a different straight line depending on where you are. But if I imagine a small change in x, I'll have a small change in y associated with it in that particular area. If I know what my x initial is, if I know where I am and how much change I have, I can figure out how much y would change because of that if I know a relationship between x and y. So this relationship between x and y will then give us a rate of change, and specifically what we're going to work on is constant rate of change. And so let's start with maybe, again, like I said, some of this seems like, oh, I did this a long time ago, this is simple. There's a lot of underlying things to investigate that maybe kind of skipped over when you learned about this the first time, because a lot of the details wouldn't have made sense. Kind of happens a lot with, when you learn history when you're this big versus when you learn history when you're in high school. You learn a lot more details of some of the same concepts, some of the same events. Same here. So talk about, all right, driving a car. Once you get on the highway, your car's cruise control set to 70 miles an hour. Great. So what does it mean that we're driving at this constant rate of 70 miles per hour? Any thoughts on that? 1 hour you go 70 miles. Is that all you can do with 70 miles an hour. No, so that's true. If you were to go 70 miles an hour for 1 hour, you would have gone 70 miles, which is a mystery to some people that I've seen videos about, and that makes me cringe. But that's what 70 miles per hour can mean. Every additional hour means an additional 70 miles traveled. So whether it's 1 hour and you go 70 miles, that's one thing. But you could go 2 hours, go 140 miles. Or, let's see, what about in 5 hours? If you traveled for 5 hours on the highway at this 70 miles an hour, how far on the highway would you have traveled? 350 miles. All right, so what if I pick a random number like a half an hour? Can we still do that? Yeah, you'd go half of 70 miles. Or if a tenth of an hour, we go a tenth of 70 miles, so 7 miles. So the fast way to describe it, and that you know more than what you typically say when you see this, or maybe you know more than what you first think. 70 miles an hour means an hour you go 70 miles. Yes, it does. And it also means a lot of other things. It means a whole array of things that any amount of time, if I gave you any amount of time, what would you need to do to figure out how far you traveled? Well, make sure the time's in hours and then times 70, right? It's this multiplication, it's this proportional relationship between the two for any additional time. So let me just say X is how much time we've been traveling wherever, but an additional amount of time traveled on the highway, let's measure it in hours. I can figure out how far I traveled if I multiply by 70. Now, specifically, to be precise about this question, for any additional time traveled, measured in hours, the distance traveled increases. It's not decreasing my distance by 70, so that change, we have to think about positive or negative. But if I have an additional amount of time traveled, I'll have traveled an additional distance. And for any additional amount of time, I'll call it dx, a change in the amount of time that's been traveled, or as my time varies through any amount, my time in the world, varies through any amount, I can figure out the distance traveled during that same interval by just times 70. And the distance will come out in miles because of the units of this 70. So this relationship between changes in one variable or one concept and changes in a second concept that's related to it with this constant rate is just this proportional relationship here. Changes in one, multiply by a number to get changes in the second. And it's the same number every time. It's not a different number based on where you are on the road or how many hours you've traveled. It's always times 70 if you're going at a constant rate of 70 miles per hour. All right, one more. Filling up the gas tank, gas is $2 a gallon. Maybe you had to pay 35 cents to use your debit card or whatever at the AM, PM, or whatever it might be. But if there's this $2 per gallon, which I put the units together like that in the second line, but typically in English we write it like the $2 first and then the per gallon afterward. But thinking about the same thing we just talked about, the meaning of this constant rate, $2 per gallon. 70 miles per hour, we can translate that. So let's see, $2 per gallon means that let's try for a wide range of applicability with this $2 per gallon.
For every gallon you spend $2.
Okay, for every gallon you spend $2, that's our first thought. That's how we can start interpreting it, and then how can we make that apply in more places or in more situations? Do I have to buy whole gallons at a time? No. Can I buy 7 gallons at a time? 2.62 gallons at a time? Yeah, whatever that number of gallons is. Yeah, multiply by 2. So however many more gallons I buy, whatever, sometimes there's extra fees and charges they tack on the front. Whatever my price might currently be, if I buy dx more gallons of gas, to explain this more precisely or to make it fit more situations, if I buy dx more gallons of gas, then to get the change in my cost, the extra cost that puts on my bank account, I multiply by 2. And using the dx in gallons and dy comes out in dollars when we do this multiply by 2. So this kind of covers instead of just saying the one that you know what it means and you know how you can use it other ways, but to actually say those other ways is to use this notation. Any additional number of gallons purchased, whether it's a whole number, a fraction number, any amount of variation in the amount of gas that's come out of the pump and into your car, multiply that number of gallons times 2, and you get the number of extra dollars that extra number of that extra amount of gasoline cost you. All right, so I want to show you one last thing, and then I'm going to make this as an assignment. Let's see, because I know it's the end of class right now. So there is in Canvas, and you might have seen this when you were in here earlier, it says Canvas Quiz 2, Definitions in Constant Rate of Change. This quiz, if you open up, has 2 questions. They'll probably take you a total of 30 seconds. You can do it now. You can do it a little bit later. It says it's due at 10:45. I'm going to change that so it's due at 11:45, just so if you're like in a hurry to get someplace else, you don't have to rush. I meant to finish a few minutes ago. But this quiz will probably take you a total of a couple minutes. I have it set to be 5 minutes. There's 2 questions about the basics of constant rate of change that you can see in your book. You can ask somebody else. This is just like a, do you know how to use Canvas quizzes, and were you in class? All right, I will see you next time.